Good afternoon, everyone. As we proceed further, we begin with our next session on navigating India's refrigerant transition, policies, technologies, and industry readiness, co curated with Indy 3. As we start, I would like to welcome our speakers to stage. Shri Aditya Narayan Singh ji, Scientist, Director, Ozone Cell, Ministry of Environment, Forest and Climate Change. So please, if you could. Next, I would like to invite Mr. Milind G. Mohile, Vice President and Head, Strategy and Growth, Triveni Turbines. Mr. Manish Shankar Das Gupta, Senior Professor, Mechanical Engineering, BITS Pilani. Dr. Santosh Saini, Principal Research Associate, AEEE. Mr. Sonal Kumar, Program Lead, CEEW. Professor Sukumar Devota, Chair, Research Committee, ISHRE. And before we start, I would like to invite Shri Aditya Narayan Singh ji for the opening remarks for this session. So please.
Speakers, panelists, and participants of the thematic session, good morning to everybody. And first of all, I would like to thank for inviting in this thematic session on navigation India's refrigerant transition policy, technologies, and industry readiness organized by the AEEE. And just I want to give the background that the Montreal Protocol, an international treaty for phasing out production and consumption of ozone depleting substances, has been addressing the refrigerant transition. And as most of you are aware, the last category of the ozone depleting substances, namely hydrochlorofluorocarbon, which is basically known as HCFC, are currently being phased out as per the accelerated phase out management plan. And this India is a party to the Montreal Protocol since 1992 and has been proactive in the implementation of the Montreal Protocol, including phasing out of the SCFC 141B as on 1st January 2020 and phasing out of SCFCs as a refrigerant in manufacturing of new equipments as on 1st January 2025, well ahead of the Montreal Protocol phase-out schedule. In the Montreal Protocol implementation, including in earlier ODS transition, that is the phase-out of CFCs, CTC, India has consciously chosen the path of environmental friendly and low global warming potential technologies. And in the country program developed during 1993, which formed the roadmap for implementation of Montreal Protocol and ODS phase out in the country. And it has been ensured that the implementation of ODS phase out activities should not adversely affect the industrial and economic growth of the country. And consumer and public interest are adequately protected. During each of the refrigerant transition, it has been ensured to have a minimum economic dissociation, and the alternative adopted are safe and sustainable. It has been further ensured that alternatives as far as possible are from indigenous sources with focus maximizing indigenous production for twin environment and economic gains. As per the agreed phase down schedule of HFCs under Kigali Amendment, India will have to complete the phase down of the production and consumption of HFC in 4 steps from 2032 onward, with reduction of 10% in 2032, 20% in 2037, 30% in 2042, and 85% in 2047, respectively. The Kigali amendments transition from high GWP hydrofluorocarbons, commonly known as HFCs, faces key issues including the availability of low GWP alternatives, including high cost, technical limitation, adaptability, including supply chain issues of the alternatives, as well as the equipment and its component, particularly for MSMEs, and the need for improved energy efficiency and safety concerns with flammable natural refrigerants. It is therefore important for a clear long-term policy to guide industry investment. Over the past few years, cooling is terms being talked globally in several fora, and cooling is a cross-sectoral issue linking with economic growth, and the rising per capita incomes, rapid urbanization across economics has led to rise in the requirement for cooling, which is both a challenge as well as the unique opportunity. This necessitates synergies in policy and action to address the cooling requirement across sectors, making cooling accessible to all, more so considering that cooling is recognized as a development need and with achieving many sustainable development goals. Recognizing the importance of cooling and the close linkage with the Montreal Protocol implementation, the MOFCC has developed and launched the ICAP, that is known as India Cooling Action Plan, during 2019, a multi-stakeholder integrated and consultative process to synergize action for addressing the cooling demand across all sectors. The ICAP development and the implementation framework demonstrate high inter-ministerial and cross-sectoral collaboration in laying out actionable pathway to provide sustainable cooling to meet the cooling needs while neutralizing the negative impacts. The recommendation of ICAP are being implemented in 6 thematic areas, namely space cooling in buildings, cold chain, domestic manufacturing and production sector, alternative refrigerants and technologies, servicing sectors, transport air conditioning, research and development. Toward promoting indigenous manufacturing of low GWP chemicals and development of robust R&D ecosystem, the MOFCC has developed an action plan for indigenous development and domestic manufacturing of next generation low GWP refrigerant cooling appliances, along with safety standards and upgradation of skill of the existing manpower for wider adoption of such refrigerants during the phase down of HFCs under the Kigali Amendment. And this includes collaboration with the 8 Indian Institutes of Technologies, Hyderabad, Kanpur, Madras, Roorkee, Patna, Tirupati, and Varanasi to promote research and development of low GWP chemicals. And the increased air conditioning and other cooling equipment has led to significant demand in the service sector, and which play a crucial role in environmental protection by reducing harmful refrigerant emission and ensuring energy efficiency. And proper servicing is a vital, the efficient operation of cooling equipment, minimizing energy consumption and supporting national commitment under the Montreal Protocol. To inculcate professionalism in the service sector, there is a need for technicians to improve technical skills, adherence of good service practices and environmental regulation, especially in handling low GWP refrigerants, and have issue relating to flammability, toxicity and safety, and adopt safe work procedures. To address this, the MOFCC, along with the National Council for Vocational Education Training of the Ministry of the Skill Development and Entrepreneurship, has finalized qualification pack for certification system for AC service technicians under the National Skill Qualification Framework of the Government of India, and which would be highly useful in formalizing the air conditioning service sectors. And the certification system has been integrated with the training of 25,000 service technicians as a part of ongoing implementation of SCFC Phase-Out Management Plan Stage 3. To further strengthen the service sector and develop a skilled workforce in the country for handling the service requirement of RSC equipment, including flammable and toxic refrigerant. The MFCC is supporting 120 ITIs through providing RSC training equipment in close collaboration with the Director General of Training, DGT MSD. And the training equipment will enable the ITIs to train the RSC trade, a student to prepare for installation and maintenance of equipment using best practices. And this initiative would also provide better livelihood opportunity for AC service technicians, particularly after the government e-marketplaces has introduced a category of trained and certified technicians for AC servicing related activities, and based on the action point finalized under the ICAP implementation framework. In addition to meeting the Montreal Protocol compliance obligation, the country towards protecting the environment has also taken necessary steps for appropriate management and disposal of refrigerant at the end of life RSC equipment through necessary provisions in the e-waste management rule. Now the country is preparing itself for the HFC phase down under the Kigali Amendment, and as a roadmap of HFC phase down is under preparation, in which all the stakeholders, including industry and closely associated. And this roadmap for phase down shall consider national circumstances for a smooth and sustainable transition for HFCs to low GWP alternative, especially by MSME, and which form a large part of industry. The roadmap will also consider the principles of earlier country program for ODSs, focusing on minimum economic dislocation and obsolescence, particularly for MSME, without adversely affecting industrial and economic growth. The hallmark for the success of the Montreal Protocol implementation in the country is the very active participation of the stakeholders, including the concerned line ministries, department, and the industry stakeholders. And while a beginning has been made, it is important that all like-minded institutions, including industry, should work following the synergistic approach to achieve the goal of the ICAP as well as the compliance obligation under the Kigali Amendment in a sustainable way without undue burden on the industry or the economy. And there is also a need for coordinated mechanism between the various stakeholders in refrigeration and air conditioning research. And as such, robust enabling platform is a key need in fostering meaningful collaboration and linkages. The expert of R&D institutions synergized with the industry effort can help achieving sustainable cooling through the indigenous efforts. Thank you very much.
Well, thank you, sir. Now I would like to invite Dr. Santosh Saini, Principal Research Associate, AEEE, for his presentation.
So thanks Vivek and Aditya sir for setting the context and the importance of the current refrigerant transition, the Montreal Protocol and the subsequent Kigali Amendment. Also highlighting the role of ICAP implementation, role of technician training and capacity building. I'm going to tell one of the initiative we are working currently ND3. Is the third phase of ND program, uh, in which we are doing all the activities related to the ICAP implementation in India, as well as the Kigali Amendment implementation. So ND3 is a program running between 25 to 29. It is built on ND and ND plus, which are running from 2016-17. In these programs, this is a consortium of various industries, academic institutions, and research organizations, OEMs, and component suppliers basically in India to build the overall ecosystem for the refrigerant transition, to support the refrigerant transition to low GWP or natural refrigerants, along with the energy efficiency and to reduce down the GHG emissions. In the program, we are doing research and studies at various academic institutions, doing knowledge exchange through seminars, workshops, and classroom activities, pilot demonstration in various applications like cold chain, heat pumps, space cooling, etc. Also doing the sectoral implementation, and cold chain is the new initiative we added in the ND3 program. So in which we focus on reducing the resources in the food value chain, reducing the food loss and waste, also improving or maintaining the quality of the food sources. So the overall aim of the project is to demonstrate scalable solutions in many cooling or cold chain or heating applications, so that these refrigerants can be easily adopted wherever required. The activities in the program you can see on the screen. So we are doing coordinated actions along with all the stakeholders, doing targeted training programs. PhD scholars are being trained along with postdoc researchers. We are working with the end users to demonstrate the viability of these natural refrigerants basically in various applications, and the academic institutions like IIT Madras, BITS Pilani, IISc Bangalore are there, along with Norwegian research entities. They are doing the test bed research, transferring it to the industries to implement it in a better way. We are also doing the market linkages between all the stakeholders. So the actors or the project partners name you can see on the screen. So few of them are from Norway, Sintef, Ocean, NTNU. One is from France, IAR, and other are Indian academic institutions, industry associations, or research bodies, research think tanks. So in the program, AEEE is particularly focusing on the horticulture cold chain implementation of these refrigerants in various applications like cold rooms, cold storages, refrigerated transports, identifying the suitable refrigerants and demonstrating it to these sites. So we are covering all the applications, including industrial refrigeration, cold storage, commercial food service, seafood processing, heat pumps, etc. Doing the field research in academic institutions, labs, transferring it to the industries, and implementing it into the field with the help of end users. Again, these are the partners. Along with this, few industry members are not mentioned in the screen, but they are also the partner of the project, where we identify them to implement the suitable refrigerant in various applications. And so my following presentations will be from various organizations. They will tell you that what they are doing in academics, research institutions, and industry to support the refrigerant transition in a better way. Thank you.
Thank you, Dr. Santosh. I would now like to invite Professor Sukumar Devotta, Chair Research Committee 2026-27 ISHRE for the presentation. I guess this is it.
Yeah, just good afternoon, because we are just past mid-noon. I'm speaking on behalf of ISHRE, although I am speaking on behalf of ISHRE and I am a member of few UNAP committees, but my views are personal. I want to disclaim that I'm not speaking on the views of the organizations I'm associated with. That's because when Santosh invited me, he said, you need not be strictly speaking what ISHRE thinks, but you should be speaking global pictures applicable to India. So I decided to speak that way. And I use some of the materials from ISHRE because ISHRE has a position paper. It's a downloadable position paper on what India has currently and what it can use in future for various sectors. So this is a position paper document which I have cut and pasted in this, and on the side I give you my personal view. So if you take domestic refrigeration now, virtually globally R600A, isobutane is the choice. Yeah, it's a A3 flammable refrigerant. It's being used globally. So there is no alternative to 600A because it's already very, very low, what we can call it as an ultra low GWP refrigerant. Then commercial refrigeration, there is a trend that because of the certain limitations on size of the refrigerant charge, people tend to use either HFOs or 290. If you are buying in India any ice cream cabinets and today or any display cabinets or bottle coolers, it is either with 290, mostly for low temperature, or if it is bottle coolers, it is with 600A, that is isobutane. So propane and isobutane is the most popular one now today, although it's flammable. But there are larger systems where there is a likely that HFOs will come into use, although it's not being used extensively. So this is a long term. Then room air conditioner, we were using 22, then we shifted to 410A, then 32, R32, HFC 32 came in, then there was a market for 290 propane. But then today almost all manufacturers use HFC 32, and except one which makes using propane. I'm happy to say that that technological support for one company which uses 290 was provided by my group, and it is the same that we provided the technological support for isobutane in the refrigerator. So this company started looking at hydrocarbons, what we call as a leapfrogging, avoiding HFC totally in their market. And if you go to so today the market is flooded with 32, R32, that is HFC 32, or to some small extent 290. And one caveat I wanted to say that R32 will not be a final solution. It has to be phased out eventually, which I'll come later. And what is the alternative we have? 290 is the only alternative which is very high energy efficient. In the market, if you go at market and look at standardization, the 290 models have the highest energy efficiency, better than any other model. Okay, now large air conditioners, because of the safety, most of the the systems will use HFO blends. HFO blends are also flammable. Not that HFOs are not flammable, but they are mildly flammable, whereas if you take 290 and isobutane, they are highly flammable. So you have to take care of safety in any refrigerant in future. So I want to give this message across refrigerant choices. No future refrigerant is likely to be non-flammable. Very few, very small sector. But if you take bulk of the applications, more than 95%, it will be flammable refrigerants in the future. Okay. The mobile AC, today we are using 134A, but it's due for, because it's under Kigali Amendment, KIPS, and we'll be dealing with that 134A AC in mobile air conditioners. But the international market has already penetrated using HFO 1234YF because Europe introduced a condition that anything more than 150 GWP cannot be used in MAC, so they shifted to HFO 1234YF. So it's possible that, and in India also they use HFO 1234YF in models where they are exporting, because many car manufacturers are now manufacturing in India and exporting. So they will be doing that. And then if you take transport refrigeration, again, HFO blends and HC290, propane. It's becoming very common in transport refrigeration in Europe, and but it is possible that it will come in a big way in India as well. And the next one is industrial and commercial. If you take cold room, it's ammonia, dominated by ammonia, and but there are possibilities you will use it with large systems because of the safety. You may do with HFO or cascaded with HFO or CO2. And HFO and their blends will be used in chillers, and that's what is going to happen. R32 is coming in a big way, but I feel that 1234ZE will come in a big way in large chillers. Commercial heat pumps, today it is all 290 because monoblock systems are developed. Even Indian companies develop these in India and export it. So commercial heat pumps could be smaller ones, space heating and space water cool heating and all that. But if you want larger systems, there are HFOs. But most of the European heat pumps are with propane or isobutane, because isobutane can work at a very high temperature. Yeah? And then industrial heat pumps could be with HFO blends. So the target for me, takeaway message, that we need to move faster than what we are doing with respect to Kigali implementation, because as per the model proposed, the 2040 will be crossing 500 GWP limit. That means by 2040, India average GWP should be 500. 32 is 675. So our 32 GWP is 675. It cannot sustain our, KIPS, Kigali implementation. So we need to start looking at natural refrigerant in big way. For room air conditioner, it's the largest refrigerant bank in India, and worldwide room air conditioner growth is phenomenal, including India. But then if you take charge, it is still the largest is in room air conditioner, and we need to have LRM in a much better way than what we are doing today. We are training people, but then if you want to know where is the refrigerant recovered and going, we have no clear answer. We have rules, but we do not have a clear answer. Where does it go? Or if you ask me, where did CFCs go? We have no answer. Where did the HCFCs go? We have no answer. It's all gone, but we have no answer. So LRM, we have to be much more sincere in future. And energy efficiency, I would say, is a big part of the India's future zero energy cooling. And we need to look at energy efficiency much more aggressively. Currently, we are, you know, putting in BE 3% annual growth in improvement, but then we should be at least looking at 4%. If you don't look at 4%, it's not possible to reach zero cooling, energy cooling by 2050 or 2070 even. Yeah, so safety is an important element, because I told you all refrigerants will be flammable, and it doesn't matter what you are looking at. But we have adopted some safety standards for appliances. BIS has adopted IEC 60335 2-40. That's the one appliance, 2-89 for commercial appliances. But we do not have still a good standard, safety standard for ammonia-based systems. If you go to fisheries or cold rooms, we do not have safety standard. And even the best of the companies operating in India, they do not follow international standard, because it's not mandatory and it's not competitive for them to follow those standards which they follow in Europe. So it is a big issue for us. We need safety standards for ammonia systems and CO2 systems. Ammonia for toxicity and flammability, and CO2 for high pressure, because the system operates around 120 to 140 bar ammonia, CO2. And we need to look at low charge ammonia chiller in a big way, because of the safety. The best way to look at safety, implement safety, is reducing the refrigerant charge. Besides looking at other things, mechanical, but refrigerant charge, if you reduce, you're increasing the safety. So we need to look at low charge ammonia in a big way, which I want to just give a message. 25 years ago, I went to a plant, ammonia plant in Oslo airport, and they were using tons of ammonia. There was no smell of ammonia in the entire machinery room I visited. This was 25 years ago. And today, many airports are heated with ammonia heat pumps. So we should be looking at low charge ammonia in a big way. And similarly, we need to do more. India is looking at CO2, but we need much more commercial activity on CO2, because CO2 is one of the best in terms of GWP. It's virtually one, and you cannot beat that. And so the ISHRE paper gives some of these points which I mentioned, has its position. Thank you very much for your patient listening.
Thank you, Professor Sukumar Devota. Next, I would like to invite Mr. Sonal Kumar, Program Lead CEW. And looking at the time constraint, I would request presenters if they could wrap their presentation within 5 minutes.
Good afternoon, all of you. I'm Sonal Kumar. I work with Council on Energy, Environment and Water. It's a policy research organization working towards impacting sustainable development at a scale using data integrated analysis and strategic outreach. And we are part of this INDI consortium since 2017, working on different aspects of refrigerant transition. Refrigerant transition, a sustainable refrigerant transition requires actions on many fronts. I will be talking about three pillars or three aspects. One is managing the refrigerant banks, that is life cycle refrigerant management, then preparing the workforce for today and tomorrow to support the refrigerant transition, and selecting the right alternative in the refrigerant transition going forward. So first I will talk about life cycle refrigerant management. So our transition will start after 2028, and then we will be reducing HFC consumption from the baseline by 10%, 20%, 30% in the next 5, 10, 15 years. So, and there are also a lot of huge amount of refrigerants having high GWP and ozone depleting potential accumulated in the existing stock of cooling appliances, and we will be further accumulating that. So how we will avoid the emission of these refrigerants into the environment, so that will be crucial to have a sustainable refrigerant transition and also avoiding its emission. So preventing leakages during installation and operation, and also at the end of life of appliances, how we recover and recycle it or destroy it safely. So that will be crucial aspect of the refrigerant transition. And we did some study on that, and our analysis shows that if we do it right, we can avoid around 2 billion tons of CO2 emissions by 2050. And for doing that, we need initiatives on various fronts like policies, standards, training of technicians, creating a reverse supply chain, so entire ecosystem of recycling, collection, aggregation, and reclamation or destruction facilities, and then ensuring a financing mechanism which finance all these things. We have already taken a lot of initiatives on these fronts. I will be talking, in the interest of time, I will be covering one aspect which is very crucial is there are a lot of actors that need to be involved, right from technician who is collecting the refrigerant or recovering the refrigerant, then collection, testing, logistics, recycling or destruction. And we need to ensure a sustainable business model for all these actors to basically sustain these activities in the long run without support from any grant and all. So that is one of the key aspects which we should focus upon. And there are mechanisms like extended producer responsibilities or carbon credits generated out of destruction of these gases or carbon tax. So, and we have adopted EPR route and we are going towards that, but this need to be ensured unless there is adequate incentives for all the actors or sustainable business model for all the enterprises, those who are involved in execution of these practices. So it will not sustain in the long run. So then coming to the second point, so it is regarding preparing the workforce. So, from the workforce, we mean that we need skilled, equipped, and motivated technicians. So they need to be trained. They need to have access to affordable tools and equipments, and also they should get adequate incentive or remuneration to basically remain motivated in this sector, because attrition is also a big challenge. So how we can ensure sufficient incentives for them, and also a career progression path in this sector, so that that keeps them motivated to remain in that. And we need a lot more number of technicians going forward. So our analysis with the refrigerants and AC manufacturer, refrigeration and AC manufacturer association shows that in the space cooling sector, currently we are requiring around 3.5 lakh technicians. That will increase by up to 55 lakh by 2047. So that means there will be a huge requirement of technicians going forward. So we already have a lot of training programs and to train them, but keeping this growing demand in mind, we need to basically ramp up or basically put extra effort in that thing. The third point I would like to touch upon is selecting the right refrigerant choices, and it basically depends on many parameters. So this Aditya sir has already covered a comprehensive view of what parameters we are looking at. Professor Sukumar Devata has also covered. So I will like to highlight one. So it involves basically technical feasibility as well as safety, like many of the alternatives are flammable or toxic, or there are other challenges, then efficiency, and then it should also be affordable for the Indian consumer. So keeping all these points, but I will highlight one issue which is currently emerging globally is the issue of PFAS pollution, so per and polyfluoroalkyl substances, and many of these alternatives, these basically convert or decompose to create PFAS into the environment, and except R32, R134A also converts to PFAS, and many of these HFOs convert to PFAS. So there is a growing concern globally around that. Many so refrigerants basically convert to trifluoroacetic acid. There are some differences in whether we should classify or categorize it as PFAS or not, but Europe categorize it as PFAS. US EPA do not categorize it at PFAS, but several of the US states, they have now categorized it at PFAS. So that is a growing concern. So we need to study that how it will be impacting Indian refrigerant transition and choices of refrigerant, because on both fronts, with how it will be impacting Indian environment and the health of Indian population, as well as also the industry, because we also export. Our industry also exports to these geographies. So if there is a ban or restriction in those countries, so how it will be impacting our industries. So we need to analyze that, and then because refrigerant transition, it requires a huge amount of effort and investment by the industry to ramp up or modernize or transform their supply chain, component manufacturing, product manufacturing, all those things. So it should not be like solving one problem is creating other, and then again we are talking about the transition. So analyzing all these things, we should think for a long-term sustainable refrigerant transition pathway. And already, we are focusing on some of the applications of natural refrigerant under the Readiness project, and these applications are already gaining pace in many of these major demand centers. So I'm showing some photographs which highlights like hydrocarbon-based cooling devices or CO2-based cooling devices, how their market is growing up in the double-digit CAGR every year in some of these Europe, USA, Japan, Australia, in these markets. So with this, I will conclude my presentation. Thank you all for listening, and we will take up questions later on. Thank you.
Thank you, Mr. Sonal Kumar. Next on stage, I would like to invite Professor M.S. Das Gupta, Senior Professor, Mechanical Engineering, BITS, Pilani.
Yeah, good afternoon, all of you. I hope this preparation time is not subtracted from my presentation time. So it's a pleasure to be with you, and then it's a privilege, definitely, to be with you. Other days I am generally surrounded with students. I bring the technology perspective of the whole thing. It's not that interesting as presentation by Sonal, because he deals with the policy matters. So I come here from representing the Indy 3 in this Indy 3 special session, where we have a couple of partners from Norway. There is a funding agency, which is Norwegian Embassy in New Delhi, who funds the program through Norwegian government. And then we are a couple of universities in India, and then policy research organizations here. Why natural refrigeration matter now is something which is possibly very important. India is not only growing in terms of the trade, MOUs or the GDPs and so on. India, the cooling demand is also one of the highest in the whole world at this point. Okay, so the direct emission is estimated to be 52 million ton of carbon equivalent as of 2024, and combined, that is from the direct emission as well as the carbon emission from the energy sources, which is majority of coal burning for India, is pegged at 156 million metric ton. See, this something which you will have to understand is that this growth and all that cannot be stopped. It is India is only now getting the, major population is coming to the mid-income level or little higher income level, and then they had been suppressing their need of cooling and comfort for generations. You cannot tell them that switch off your AC or don't run the refrigeration system or so on. It will be there. That's the developmental. So industry, housing, mobility, etc. will grow, and then associated carbon emission will grow. You just cannot avoid it. The per capita emission is much lesser in India compared to all other countries, progressive countries, as we know. So the direct emission part, which is from refrigerant leakage, and then has to be the target. Okay. Which is basically not developing any developmental service, and that is what has to be targeted, and that's what technologically we want to target here. So if we look at the status of R&D in India, where we are and where we are strong, we are basically strong in many fields, and then what is holding us in catching up this natural refrigerant as a wildfire is not the technology. It is basically deployment capability and then trained manpower and then things like that. Okay, and then maybe some fiscal policy or policy matters which are there. India's natural refrigerant R&D has moved from the feasibility level to the engineering level. Actually, if you look at India 3 project, the essential of this is technology deployment and then technology demonstration, which we have done at our member universities as well as many of the industries. We have set up a CO2 ammonia cascade system in Kochi, two of the cold chain factories which exports fish, frozen fish, and then they are very big. This recent trade MOUs with the EU, etc., will actually help us or pressurize us, because EU, as you know, are very sensitive to the amount of carbon emission from the downstream processes in the whole supply chain. They like the supply chain to be green, and then if our supply chain is not green, we'll face a problem, even though there is a target how much we can export, but then there will still be problem. So these will possibly in very near future will come to us and help us, and then as a policy matter they will come down. So CO2 R744 we are ready with supermarket implementation, which is very large implementation, or cold storage implementation, or heat pump. We have done it under all of this. Maybe supermarket in Leeward, we have not done it yet, but all the others we have done. Okay. Hydrocarbons, for example, R290, R600A, as Professor Devata also mentioned, small cold room, bottle coolers, domestic split ACs, it is mature. Technology is mature, we are capable. Ammonia for ice production, industrial refrigeration, the systems are there and we are doing. R744, R717 cascade, which we have done for a couple of industries, now very large scale, industrial deep freezers, etc. In the universities also, in all of the universities, we have technology demonstration units. For example, in BITS Pilani, we have a R290 unit, which is about 13 kilowatt or 3.5 TR, and which is for producing flake ice for small boat fishing unit. Okay. If you look at what is holding us, this safety issues which are there is one of the concern, is a design problem, and it is not a refrigeration related problem. You have to understand that. We have already tamed. There are a lot of other, more flammable substances. For example, cooking gas. Our housewives are we're dealing with every day, every houses. Okay, there is petrol in your car which you are dealing, and it's a design problem essentially. So CO2 or R290, which is the pressure problem, these are all design problems, and then flammability issues, and then they can be tackled with design, and it is not a refrigeration issue as such. So application readiness, what is ready, deployable at immediate scale are many. We need not, essentially I want to focus, or I want to emphasize that we need not get into the trap of HFOs as of now, because we can directly leapfrog from our existing legacy system to the natural refrigerant system, and we are capable of it. Technology is there. We need not ourselves get locked down into a HFO as a transition system, because they have PFAS related issues which we get locked in, the microplastics and all that for a long time. Is not required. We had been seen that kind of examples are there, very mature in India. For example, in Western world, there was a long era of, car telephone. We had not had this car telephone business at all. We had the era of no car or no telephone in a car, to a era now, which is car with telephone in every occupant's passenger's pocket. Okay, so we have leapfrog there. We didn't have that. So there is no need to get into the HFO era, because we can leapfrog directly into natural refrigerant, which is the end point or the ultimate refrigerant, as we believe, because it is a biosphere gas ultimately. Okay, so to go into the natural refrigerant, we cannot think of a simple 4-component refrigeration system as we have done elsewhere. We need system level integration, system level design, which we are involved, many others are involved, where there are a lot of technologies, for example, ejector-based technologies, for example, subcooling, for example, pressure exchange. It's a new technology. We have some papers around that, which are getting mature. And then also we can contain by design the flammability and related issues. We have done it in many other places, for example, cooking gas, for example, petroleum, diesel, etc., etc. We are doing it, or in industries which are dealing with flammable gases, more flammable gases, naphthas, and so on. We can do it, okay? So that's the end message I like to, there's a limitation of time, that the end message I like to carry. That is, for domestic refrigeration, R600 is fully mature as of now. For commercial refrigeration, R290 or 744 are in scalable phase. We have systems or units deployed within India. Industrial cold storage, R717 is mature and also evolving in terms of low charge refrigerant system. ACs and heat pumps, we are seeing the rapid transition underway, and transport refrigeration is basically under strong pilot stage right now. There are some barriers which we recognize, which is a kind of skill gap more than technology gap as of now. Installation, services, technology training, fabrication, these are challenges. Financial risk perception is there, which possibly misplaced a little bit. And fragmented standards are enforced here right now in India, which needs to be enforced. Okay? There are quite a few enablers. For example, industrial ecosystem, which is there in India, a large system, there are large number of fabricators distributed all over India, major cities and nearby. That's a very good enabler. The policy enablers at this point are Make in India, ICAP, and so on. And their export competitiveness are there, which possibly will come, and then more incentives will come through these trade regulations, which are coming up, I believe, within next 1 year. And we see a great growth in natural refrigerant. Thank you.
Thank you, Professor Das Gupta. We are already there with the session timings. Our next presenter, I would like to invite Mr. Milind G. Mohile, Vice President and Head Strategy and Growth, Triveni Turbines. It's a very humble request, sir, if you could wrap your presentation as soon as. Yeah, please.
I'll try. Thank you. So let me jump right into it. Okay, this is jumbled, the presentation. But anyway, so I like history, and that's why I like to study it. And this is a brief history of refrigerant transition over the many years that we have seen. Now I will not go through the details because we have only limited time. But what I want to highlight is every stage where we were in terms of refrigerants, we had some or other challenges. Initially, when we started it all, we had challenges of flammability with the initial refrigerants. Then, of course, the CFCs took over and they had a big run. And now we are at a stage where we all are talking about natural refrigerants and low GWP refrigerants, and for a good reason. So why this new beginning is required? If you understand direct and indirect emissions of CO2, that is, what we have done over the years is we have effectively lowered the indirect emission, that is electricity consumed, because we have efficient refrigeration systems, compressors, equipment which are consuming less energy. Also, we have a cleaner energy mix now with the renewables put in the mix. So the overall energy in terms of CO2 emission has improved. Now, for the direct CO2 emissions also have reduced because we have now, again, systems which are leak-proof. So this is what has happened over the years, that the percentage of the direct emission is reduced overall. If we continue in this fashion without transitioning to natural refrigerants, then we can, again grow that percentage. So, and our energy requirement is also growing by every year. So this is going to get us into a position where all the gains that we have made in designing efficient equipment, in having a very efficient energy mix, all those gains are going to be lost. So the energy transition from that point of view is very essential. So when we talk about this new beginning and this new refrigerants, what are we talking about? So I essentially classify that into a few properties or few features that we want to look in the refrigerant. The toxicity, flammability, yes, as low as possible. But as the previous speakers have said, there is going to be that problem because a lot of these natural refrigerants are hydrocarbons, are ammonia, CO2, which has a pressure issue because those CO2 systems are high pressure. So it depends on the application where we would fit the best refrigerant. In terms of ODP, it has to be 0, no compromise, and we have solutions available. So we can do that. GWP, when we say, it has to be less than 5, ideally 1, and we have solutions for that as well. And in terms of working properties, the range, the envelope of the particular refrigerant, and also the heat capacity, all those things matter. So these are the parameters that I'm looking for when I'm talking about the new refrigerants. Of course, there are these factors that affect that, and I would like to go through that. Again, I'll not go through these details because previous speakers have already covered the Kigali amendment and all that, India Cooling Action Plan. I just want to highlight this budget, which just came out a few days ago. This has a provision for 20,000 crore outlay for CCUS. It has a provision, it talks about cold chain and refrigeration for boosting our agriculture and healthcare setup. And also the district cooling as as an infrastructure and urbanization. So these are the policy tailwinds that we have right now, which can push us towards bigger adoption of natural refrigerants, and we should continue in that. Now, of course, when we are talking about that, the safe and green transition is important. I have just put some examples there of the refrigerants on those parameters that I talked about earlier. My takeaway from that is where the application suits, the CO2 is the best refrigerant because it is neither toxic nor flammable. And of course, on the ODP and GWP criteria also it fits best. So wherever it can fit, that's the best. On the heating side, butane, isobutane, those are some of the good options. On cooling side, propane, ammonia are good options. Ammonia can be combined with CO2. And of course, HFOs are good alternatives where none of this can fit. So HFOs should be the kind of a last resort. Now, these are some of the applications where we have worked on industry problems. So we have been building CO2 heat pumps for some time now. We had built one for Indian Navy. We have built one for ourselves to demonstrate and show that we can, do that. We have a test facility also where we have tested this 100 kilowatt CO2 heat pump. And from the industry now, on the heating and cooling side, wherever we have got the inquiries and requirements, we have worked out these solutions. So what I'm trying to put out here is it is possible to scale, to provide a solution for the industry with natural refrigerants. I want to also point out the refrigeration, cold storage. There is the ammonia and CO2 cascade, which is also possible. So finally, I want to come to a point where we discuss the roadblocks or the challenges we have ahead, the enablers that we want to be in place. Of course, the energy advisories, this is somewhere the energy audit can help. A lot of countries have regulations and have support from government to perform energy audits, not only at big companies, but also at smaller organizations. And that can help identify where we need to fix the energy gap. Supply chain readiness, I was sharing with Jayanta ji earlier that we have this challenge of supply chain, because when we are talking about CO2 heat pumps particularly, these are high pressure systems. We don't have manufacturing ecosystem in India right now. So how can we put some kind of incentive for them to have a manufacturing, assembly, and testing facility in India so that we have the local supply chain available? Early adopters incentive, like PLI, there can be some kind of incentive for manufacturing of this equipment or some kind of a scheme for people who adopt these energy efficient solutions. And of course, the standards and codes, which earlier speakers have also touched upon. And finally, the skills and safety, because these natural refrigerants come with certain risks. We know those risks are. We know the control measures also for those risks. How do we train people to adopt these kind of solutions in scale? So that is a final challenge. So that's it from my side. Of course, we have no time now, but I would be happy to take any questions after this session. Thank you.
Thank you so much, sir. And I would also like to thank all the speakers for the insightful presentations. Due to constraint of time, I would request if there are any questions, you may take it offline during the networking lunch with the respective speakers. Moving forward, if I could call all the speakers and the presenters for a group photograph, please. Thank you so much to the speakers for the time. Thank you.